Imagine this. You are flying on a spaceship in deep space. Outside the porthole are billions of stars, glowing galaxies, and the familiar, beautiful cosmos. And suddenly, an ideal sphere of complete, absolute darkness appears right in front of you. The light of the stars behind it doesn't just vanish. It distorts and bends around this darkness like a lens, forming a sparkling ring around the black disk. This isn't a rift in space. It's not a portal to another dimension from a sci-fi movie. This is a place where the stretched canvas of our universe is torn to shreds. This is a black hole. In this video, we will take a journey to a place where time stands still. Physics breaks down, and our usual concepts of space, past, and future swap places. We will trace their path from their birth in the fires of dying stars to the very edge of the abyss, the event horizon, and peer into what science cannot yet fully explain. No complex formulas, just the pure magic of reality. Let's go. The first and most important thing to remember: a black hole is not a hole in the literal sense. There is no emptiness inside it. On the contrary, it is the densest and heaviest object in the universe. To understand how it works, let's recall Albert Einstein's greatest insight. He realized that space and time are not just a static stage where events take place. They are a single, flexible fabric, space-time. Imagine a huge, stretched trampoline. If you place a tennis ball on it, the trampoline will sag slightly. Place a heavy kettlebell on it, and the resulting depression becomes deep. All the small balls on the trampoline will start rolling toward that kettlebell. This is what we call gravity. The Earth warps space-time around itself, which is why we don't fly off into space. The sun warps it even more, keeping all the planets in orbit around it. Now let's conduct a thought experiment. Let's take our sun, a giant sphere 1.5 million kilometers in diameter, and start compressing it. We compress it to the size of Earth. The dip in the trampoline becomes deeper and sharper. We compress it to the size of a city. And finally, we compress the entire sun into a sphere just 6 kilometers in diameter. At that moment, the incredible happens. The mass remains the same, that of the sun, but it is concentrated in a tiny point. The dip on our space-time trampoline becomes infinitely deep and steep, to the point where the fabric simply rips. A gravitational well forms with a steepness from which nothing can ever climb out. The gravitational pull on its surface becomes so immense that the speed required to escape it exceeds the speed of light. And since nothing in our universe can move faster than light, nothing can escape from there at all. Not atoms, not rockets, not light itself. Where do they come from? From death. Black holes are the ghosts of dead stars. Every star throughout its life wages a continuous billion-year war with itself. On one side is gravity, trying to collapse the star into a point. On the other side is the colossal pressure of the thermonuclear reactor in its core. Hydrogen turns into helium, releasing enormous energy that pushes the star outward from within. As long as there is fuel, the star remains in perfect balance. Our sun has been living like this for 4.5 billion years. But fuel doesn't last forever. When a supermassive star, at least 8 to 10 times more massive than the sun, runs out of hydrogen, its agony begins. The star starts burning helium, then carbon, oxygen. At the very end, iron builds up in its core. During the fusion of iron, the reaction no longer releases energy. It absorbs it. The thermonuclear engine stalls in a matter of seconds. Internal pressure vanishes. Gravity wins instantly. The star's massive outer layers fall toward the core at a quarter of the speed of light. A colossal explosion occurs, a supernova. In that moment, a single star shines brighter than an entire galaxy of hundreds of billions of stars. The outer shell is blasted into space, but the core instantly collapses under its own unbearable weight. If the remaining core is heavy enough, nothing in the universe, no force of interatomic bonds, can stop this collapse. Matter falls in on itself. A stellar mass black hole is born. Let's examine the anatomy of this cosmic monster. A black hole has only 2 key features, but they are precisely what drive physicists crazy. The event horizon. This is not a solid surface. It is not a wall or a shell. The event horizon is the point of no return, an imaginary spherical boundary around the black hole. Imagine you are rowing a boat on a river approaching a waterfall. While you are far away, you can easily row against the current. If you'd like to see more videos in this format, please hit the like button and subscribe to the channel. It really helps boost the video's reach. Let's keep going. As you get closer, the river speeds up. You have to row harder and harder. But there is a point where the speed of the river's current equals the maximum speed of your boat. If you cross that line, it's over. No matter how powerful your oars or motor are, the river will inevitably sweep you over the edge. The event horizon is that exact line. Beyond it, space itself rushes toward the center of the black hole at a speed greater than the speed of light. Crossing it, you feel no impact or barrier. But from that moment on, all your paths in the future lead in only one direction, toward the center. There is no way back, because that would require turning back time. Singularity. And what lies at the very center? The singularity is the heart of a black hole, a point, or a ring if the hole is rotating, where the entire huge mass of the star is compressed into zero volume. Think about this. The mass of millions of suns in a point without dimensions. This means the density there is infinite. Gravity there is infinite. And right here, modern science gives up. When infinites appear in physics equations, it means our mathematics breaks down. At the singularity, Einstein's general theory of relativity collided with quantum mechanics, and both were defeated. Time simply loses its meaning there. Physicists honestly admit, we don't know what happens inside a singularity. This is the edge of our map of knowledge. Now let's imagine the most exciting and terrifying scenario. You jump out of the ship in a spacesuit and fly straight into a black hole. Your friend stays at a safe distance watching you through a telescope. What will you both see? This is a striking paradox of the relativity of time. Outsider's perspective. For your friend, the black hole's gravity begins to drastically slow down time around you. As you move toward the event horizon, your friend will see you moving slower and slower. Your voice over the radio will turn into a low, drawn-out bass. The light reflected from you will lose energy due to gravity, gravitational redshift. You will begin to turn red, then become infrared, then microwave. In the end, from your friend's perspective, you will freeze right at the event horizon, gradually fading away. They will never see you cross the boundary. To them, you will remain there forever, sealed in a frozen moment of time. Your perspective. For you, however, everything will be completely different. Your clock ticks absolutely normally. You don't freeze. You are rapidly plunging downward. If the black hole is small, stellar mass, a process with a very funny yet terrifying name awaits you: spaghettification. Because you are falling feet first, your feet are closer to the center than your head. With a small black hole, the difference in gravitational pull between your feet and your head will be catastrophic. Gravity will start stretching you vertically and squeezing you horizontally. You will literally turn into a long strand, spaghetti, even before you cross the event horizon, and you will be torn apart into atoms. But if the black hole is supermassive, the gravitational tidal difference at the edge is minuscule. You will cross the event horizon without even noticing it. No flashes, no sirens. However, looking back, you will see something incredible. You will see the entire history of the universe behind you, compressed into a bright, glowing point. The entire future of the cosmos will flash before your eyes in seconds due to extreme time distortion. And ahead of you, only the absolute darkness of the singularity awaits, an encounter that cannot be avoided. Astronomers have discovered that black holes come in different calibers. They are not just lonely wanderers, stellar mass black holes, from 3 to 100 masses of the sun. There could be hundreds of millions of them in our galaxy. Supermassive black holes, the true kings of the cosmos. Their masses range from millions to billions of suns. They live at the very heart of almost every large galaxy. At the center of our Milky Way right now lies a monster named Sagittarius A star. Its mass is 4 million suns. It acts as a gravitational anchor around which our entire cosmic home revolves. Primordial, primary black holes. Hypothetical microscopic ones the size of an atom, but with the mass of an entire mountain, which could have formed in the first fractions of a second after the Big Bang. If they are invisible, how do we find them? It's a task similar to detective work. We don't see the invisible person, but we see the dust they raise and the tracks they leave behind. Accretion disks. When a black hole feeds on a neighboring star or gas cloud, the matter doesn't fall in right away. It swirls into a giant whirlpool, an accretion disk. Due to friction, the gas accelerates to near-light speeds, heats up to millions of degrees, and begins to glow incredibly bright in the X-ray range. Stellar dances. We observe